Okay, so let's get started. So we're going to start with chapter 5. Believe it or not, this is going to be the last chapter in this course. It's a rather long chapter though, so it might take some time for us to finish it. All right, so in chapter 5, we'll be talking about solutions. And I think we discussed very briefly in an earlier chapter what solutions are when we were talking about physical changes. I forgot what chapter, I think that was chapter 3 or 4. In any case, we're going to delve into it in more detail. So let's start off with the definition of a solution. And a solution is basically a mixture, a homogeneous mixture of two or more substances. All right, and I'm quite sure we can think of examples of solutions in our everyday lives. And we're going to see some examples shortly. But before we do that, let's talk about the different components of a solution. So any solution that you will encounter will consist of two parts. You have what is known as a solute, which as stated here is a component that is dissolved or is the least abundant component of the solution. And then you have the solvent, which is the dissolving agent or alternatively, the most abundant component in a solution. All right, so for example, if I had a solution of, let's say, let me do my pen thing. So let's say, for example, I have a solution which is made up of 80, oops, okay, what's going on here? Okay, I don't know why I'm not able to write on the screen. Oh, okay. So let's say you have a solution of, let's say, 80 mils of ethanol and 20 mils of water. Then the solvent is going to be the ethanol, and the solute is going to be the water. And the reason why is because the ethanol in this mixture is greater in terms of the amount present in the mixture, 80 mils compared to 20 mils. All right, so if you have two liquids or two gases mixed with each other, then that's how you determine which is the solvent and which is the solute. Okay, so let me go back to my pointer function here. So this slide here basically gives you a comprehensive list of the different types of solutions that can be made. So you can have, for example, a solution made up of two gases, in which case the phase of the solution will be a gaseous phase. And a good example of that is the air we breathe. The air we breathe is basically mostly nitrogen. If I remember correctly, about 80% nitrogen, and then you have oxygen, and then you have some other gases. So that's a mixture, which is a solution. You can also have a solution made up of a gas dissolved in a liquid, in which case the phase of the solution will be liquid. And an example of this would be soft drinks or sodas, you know, like your 7-Up and your Mountain Dew and Coca-Cola and so on. In those cases, the gas would be carbon dioxide dissolved in water. So that's why these solutions are called the carbonated beverages. Then we have the possibility of liquids being both a solute and solvent in a solution. I mentioned one example earlier, a mixture of ethanol and water. Another example here is antifreeze. Antifreeze is, of course, that substance that you pour in your radiators so as to prevent your car engine from overheating during the hot weather or freezing under winter conditions. And the actual makeup of antifreeze is mostly a compound known as ethylene glycol dissolved in water, all right? The effect that ethylene glycol has on water is that it lowers the freezing point and elevates the boiling point. So therefore, that's the reason why antifreeze is very useful and very important when it comes to preventing an engine from either overheating or being frozen up during the winter time. Okay, Another example here of a solution is one that is formed between a solid and a liquid. So if you add a solid, which is soluble in the particular liquid, then you're going to end up with a solution in a liquid phase. A good example of this would be salt water, where the solute would be sodium chloride and water would be the solvent. Now, the next one is something that you don't meet every day around you in nature, but it does happen, especially in certain chemistry labs, especially in organic chemistry. You can have a solution where you have a gas dissolved in a solid. This is oftentimes seen when you have some special reagents that are made, such as the example that is shown here. You can actually have a combination of hydrogen dissolved in the metal platinum. And that reagent can be used to carry out certain reactions, which I won't get into right now. So you can have a gas dissolved in a solid, and then finally you can have a solid dissolved in another solid, such as brass, right? Brass is an alloy which is made up of copper and zinc, right? So basically brass is considered to be a solution of those two metals. Okay, so these are basically all the possibilities in terms of the different types of solutions that one can encounter. Okay, so let's talk about the properties exhibited by true solutions. So as we said before, a solution is a homogeneous mixture of two or more substances. And one particular characteristic of a solution is that it can have a variable composition. And what that means is that literally the composition of the two components or more components in a mixture, you can have literally an infinite number of possibilities in terms of the proportions of the different components in that mixture, all right, in that solution. Now, in terms of the particle size of the different substances involved, what you find is that the dissolved solute will be at the molecular or ionic size, depending, of course, as to whether or not you're dealing with molecular compounds or ionic compounds. Another property that is displayed by true solutions is that they can be either colored or colorless, and it is usually transparent. So usually you can actually see through the solution. So as stated here, in a solution, what you'll find is that the solute will be uniformly distributed throughout the solution, and therefore it will not settle out. So in other words, if you have a solution, let's say, for example, salt dissolved in water, you mix it, you make sure that all the salt particles that you can see disappears, and then you leave it to stand and wait a while. And in fact, you'll be waiting forever, because what will not happen is that the salt will basically come back out of solution and settle to the bottom, all right? So therefore the salt will remain in solution. As long as the water is not evaporating, the salt will remain in solution pretty much forever, unless you do something to get rid of the water, all right? So that's true for every true solution, all right? Now, even though that's the case, it is still possible to separate a solvent from the solution by some physical means. As stated here, one possibility is evaporation. So again, going back to the salt solution example, you can actually separate the water from the solution by heating the solution and evaporating the water, and the salt will be left behind. We talked about the fact that the particles in a solution are of the molecular or ionic size. And in terms of the actual numbers reflecting these sizes, the particle size range from 0.1 nanometers to 1 nanometer, or if you want to express it in centimeters, 10 to the minus 8 centimeters to 10 to the minus 7 centimeters. So that gives you an idea as to how small the particles are. Obviously, these particle sizes are too small for the naked eye. So basically, this is what happens when you have the formation of a solution. You have your solute, it's added to the solvent, and you may get a color change due to the color of the solute if the solvent is water, and you end up with a solution being formed, all right? Okay, so let's talk about this term solubility, which is basically a way of expressing the maximum amount of solute that is present in a given amount of solvent, all right? That's basically what the solubility is. It is the amount of solute that will dissolve in a specified amount of solvent. So just to give you some examples of different solutes and their solubility in water, we have sodium chloride here. Its solubility is, as you can see here, at 20 degrees, 36.0 grams of sodium chloride per 100 grams of water. And if you were to increase the temperature from 20 to 50 degrees, you'll see that there's a slight increase in the solubility to 37.0 grams of solute per 100 grams of water. And you see some other numbers being shown here. And what you'll notice, if you look at these numbers and you compare the temperature, the solubilities at the two different temperatures, you see that the solubility increases with temperature, right? And that is true for most solid solutes that are dissolved in, that are soluble in water. What you'll find is that, generally speaking, with some exceptions, that the solubility will increase with increasing temperature. So let's talk about some terms that are usually associated with the extent of the solubility of a solute in a solvent. And these are, of course, relative terms, right? You can have a solute which is very soluble in a particular solvent, or you can have it simply being described as weak soluble, so therefore not as soluble as in the first case, or you can describe it as being moderately soluble in a solvent, or it can be slightly soluble. In other words, only a small portion of the solute will actually enter into the solution. And then finally, you can have the other extreme where the solute is simply insoluble in the solvent. So these are just relative terms to describe qualitatively the level of solubility of a solute in a solvent. Now, in terms of the solubility of liquids, there are two general terms that are used. You have miscible and immiscible. So miscible liquids are basically liquids that are capable of mixing and as a result forming a solution which is homogeneous. So an example of that is the example of methanol or methyl alcohol and water. So you can mix methyl alcohol and water in different proportions and you're going to end up with a homogeneous solution. So it doesn't matter if you mix, let's say, 10 mils of methanol with 90 mils of water or the other way around, you're still going to end up with a solution, all right? On the other hand, you can have two liquids that are not soluble in each other, and we say that these liquids are immiscible. In other words, they will not mix. So an example of that would be oil and water. So if you take oil, like for example, cooking oil, and you add it to water, what you're going to find is that you have the formation of two layers. Because water is more density, water will be at the bottom and oil will be at the top, and you can actually see the distinction between the two layers, all right? So we say that such a mixture is immiscible, all right? So that's the difference between a miscible and immiscible mixture of two liquids. Okay, so this chart here gives you basically a summary of the solubility of different ions. Now, there is a chart that I have provided in Canvas, which is more comprehensive. So let me just show you what that looks like. Let me go to the Canvas shell. And let me go to Files. And let me go to, where are the tables? Tables. And then let me go to Tables Chemistry, Download. And then let me scroll down. And the table I'm referring to is this table right here, all right? So this table summarizes the different properties of different ionic compounds, right? And you can use this to make predictions as to a particular ionic compound being soluble in water. So just to give you an example, the first line says, almost all nitrates, acetates, perchlorates, group 1A metal salts, and ammonium salts are soluble. So basically, any ionic compound which fits this criteria right here, you can rest assured that it will dissolve in water, all right? So you can refer to this table if you want to make predictions about whether or not a particular ionic compound is soluble in water. And I think that this table is better than the one that is shown here, all right? I mean, you can still use this, but I don't think this table actually shows all or as many possibilities as the table that I showed you earlier. Okay, so let me move on from this and talk about the different factors that will affect the solubility of a solute in a solvent. Excuse me. Put water here. Okay, so the type of factors that would affect the solubility of a solute is dependent in turn on several factors, which would include whether or not you're talking about the gas, I'm sorry, whether or not you're talking about the solute being a gas or a solid or a liquid. But let me list the different factors which affect the solubility of a solute in a solvent. And these are the main factors. One would be the size of the ion or the atomic size, depending on whether or not you're dealing with molecules or ionic compounds. The type of interaction that occurs between the solute and the solvent, and temperature. So these are the different factors that affect the solubility of a solute in a solvent. So let's talk about how the nature of the solute and solvent affects the solubility. Now, there's a general rule that is used for predicting solubility, and it says like dissolves like. And what does that mean? It refers to the polarity of the solute and the polarity of the solvent. And what you'll find is that when it comes to polar solutes, they tend to be more soluble in polar solvents compared to non-polar solvents. So for example, you cannot get anything more polar than sodium chloride. Sodium chloride is an ionic compound, and therefore it is very polar. And then what you'll find is that sodium chloride is soluble in water, which is a polar solvent, all right? Now, if you look at the solubility of sodium chloride in ethanol or ethyl alcohol, you'll see that ethyl alcohol will dissolve sodium chloride slightly. And that's because ethyl alcohol is not as polar as water. So therefore, the solubility of sodium chloride would be less in ethyl alcohol compared to water, all right? And then finally, when it comes to non-polar solvents, such as ether and benzene, what you'll find is that sodium chloride is totally insoluble in either solvent, all right? So basically, this demonstrates the like dissolves like rule of thumb. Basically, because sodium chloride is polar, it will dissolve in a polar solvent such as water, but it will not dissolve in non-polar solvents such as ethyl alcohol or benzene. Okay, so this is just showing you the direction in terms of solvent polarity increasing, going from the ether and benzene up to the water. So therefore, as the solvent polarity increases, the solubility of sodium chloride increases. Okay, so what happens at the microscopic level when sodium chloride or any ionic compound dissolves in water? Well, this picture here basically represents what happens. So just to explain what the different models represent, this represents a water molecule, the orange spheres represents the sodium ions, and the blue spheres represents the chloride ions. So here we have a structure of sodium chloride right here. As we learned earlier, sodium chloride has basically a crystalline ordered arrangement of the different ions present. And what will happen is that the water molecule will have a strong attraction for the sodium and chloride ions, and therefore pull these ions away from the general structure of sodium chloride. So for example, you see these three water molecules pulling away the sodium ions away from the sodium chloride, and you see these three water molecules pulling away the chloride ions as well away from the sodium chloride, all right? So basically, what is happening here is that there's a stronger attraction of the water molecules for the ions compared to the ions' attraction between themselves, all right? And therefore, basically what happens is that the sodium chloride will dissolve in water as a result. Okay, so that's basically what happens when sodium chloride dissolves in water. And this is true for pretty much any ionic compound which is soluble in water. Okay, so this is just basically describing what's happening. There's this term called hydration. Hydration is basically where the water molecules are surrounding the ions, in this case, sodium and chloride ions. So therefore, that's what we mean by hydration, or that the fact that the ions are hydrated. Okay. On the other hand, nonpolar compounds, they tend to be soluble in nonpolar solvents compared to polar solvents. So for example, benzene is nonpolar, and therefore it is insoluble in water, which is polar, right? It is soluble in ether, which is nonpolar, and therefore that's a trend that you'll observe when it comes to a nonpolar solvent such as benzene, right? The solubility will increase as the nonpolarity of the solvent increases. Okay, so that's one effect. Now, another factor that we're going to look at is the temperature. How does temperature affect the solubility of a solute in water? So what you'll find is that most solutes have limited solubility in a specific solvent at a fixed temperature. So basically what this is saying is that if the temperature is fixed, then the solubility of a solute in a particular solvent will be fixed, all right? But if you change the temperature, then that can affect the solubility of the solid, if the solute is a solid in a liquid. And what you'll find is that for most solids dissolved in a liquid, an increase in temperature will increase the solubility of that solid, right? And that is generally true. There are some exceptions to this, as we're going to see shortly, right? As stated here, some solids increase in solubility only slightly with increasing temperature, and then you have some others where the solid's solubility decreases with increasing temperature, all right? Any point on the solubility curve represents what we call a saturated solution of that solid, all right? So this is basically a plot on the y-axis of the solubility versus the temperature on the x-axis, all right? So what you're seeing here is the plot for different substances. And as I mentioned before, what you'll find is that the solubility generally increases with temperature for most substances. So that is true for potassium nitrate. That's true for, sodium nitrate. That's the line for sodium nitrate. This is the line for potassium nitrate. This line here is for ammonium chloride. This line here is for potassium chloride. This one is for copper 2 sulfate, and so on and so forth. Sodium chloride, this line here, you'll notice that there's an increase, but the increase is very slight. Now, there are few solid substances that are, their solubility decreases with increasing temperature. And one of them is demonstrated by this line right here, lithium sulfate, right? So lithium sulfate is one of the few ionic compounds whose solubility decreases with temperature. And there's a reason for that, which I won't get into at this level. It has to do with some thermodynamic factors, which is above our level here of discussion. And so that's basically the general trend that you observe when it comes to the solubility of solids in solvents as the temperature affects it. As the temperature increases, the solubility generally increases. Now, you'll notice that we have two plots here, one for hydrogen chloride and one for SO2, right? Those are not solids, those are gases. And what you'll find is that as the temperature increases, the solubility of those gases decreases, all right? So as you can see, in the case of gases, the trend is opposite to what is generally true for solids. As you increase the temperature, then the solubility of the gas will decrease, and that is not true when it comes to solids. Solids generally increase in solubility when the temperature increases. Okay, so let me just skip all this here. Okay, so these are just some numbers for different substances and their solubilities at 0 degrees and 100 degrees. And as you can see here, in all these cases, the solubility increases with temperature. Some not to a great extent, as you can see in the case of lithium fluoride. The increase is slight, but it still increases. from 0.12 at 0 degrees Celsius to 0.14, what it says here at 35 degrees. Or if you look at sodium fluoride, again, there's not that much of an increase. Same is true for sodium chloride, but in the case of sodium bromide, there's a larger increase from 79.5 to 121 degrees Celsius, or I should say, I'm sorry, 79.5 grams per 100 grams of water to 121 at 100 degrees Celsius. Okay, so basically that's what is observed generally speaking, an increase in solubility as the temperature increases. And that is true for solids or salts and their solubilities in water. So as we said before, as I explained in the chart with the two gases, what you'll find is that the solubility of a gas in water usually decreases with temperature, right? And we can explain this using the kinetic molecular theory. Basically, what the kinetic molecular theory says to explain this is that for the gas to dissolve, it must form some strong association with the molecules of a liquid. But when the temperature increases, the molecules, the gas molecules, gain kinetic energy and therefore will have enough energy to release itself from the association with the water molecules and therefore escape. So that is what is being demonstrated by these two lines, these blue lines here, one for the hydrogen chloride and the other one for the sulfur dioxide. Okay, let me see here. So yeah, so this is the decrease in solubility that is observed for gases as the temperature increases. Okay, sticking to a discussion of gas solubility in water, we can also find out or identify the fact that the pressure of the gas will also have an effect on its solubility, all right? So what you'll find is that as the pressure changes, the solubility of the solids in liquids does not change by much, and neither does the solubility of liquids in liquids change by much either. But when it comes to the pressure changes with respect to gases, that can have a great effect, a tremendous effect on the solubility of these gases in liquids. In fact, it turns out that the solubility of a gas in a liquid is directly proportional to the pressure of that gas above the liquid, right? So basically, what we're saying here is that if you were to double the pressure of the gas above the liquid, then that also doubles the solubility of that gas in the liquid. So just to demonstrate this, let's say you have this liquid here and you have this gas, looks like chlorine here. And let's say all of a sudden you double the pressure by doubling the number of molecules of the gas above the liquid surface. Well, what that means is that the amount of molecules will be doubled within the liquid itself. So therefore the solubility of the gas will double as well, right? So basically that's the relationship between the pressure exerted by the gas above the surface of a liquid and the solubility of the gas in the liquid, all right? And in fact, that is known as Henry's law, which for those of you who plan to do general chemistry too, you're going to learn more about that in great detail because you can do some calculations involving Henry's law. Okay, now let's talk about the distinction between saturated, unsaturated, and supersaturated solutions. All right. So we talked about the fact that the solubility of a solvent in a solute, in a given amount of solute, remains basically constant if the temperature is constant. All right. So when you have this particular situation where the solution has the maximum amount of solute that can remain in a solution for a given amount of solvent, we call this solution a saturated solution, right? So basically what this means is that for a saturated solution, if you try to add in more solute to it, then the solute will not dissolve because it has reached its limit in terms of the maximum amount of solute that can be in the solution, all right? So basically in a saturated solution, what you're going to have are two processes that are occurring simultaneously. You're going to have the solute, which is crystallizing out of the solution. In other words, you're going to have the solute coming out of solution to form the solid solute, and then you're going to have the solid solute dissolving into the solution. So basically, you have this back and forth taking place between the undissolved solute over here and the dissolved solute. So basically, you're going to have this back and forth situation where the rate of the process going from dissolved to undissolved will be equal to the rate of the process going the other direction. All right. In other words, we have a state of equilibrium between the dissolved solute and the undissolved solute. All right. So that's what's happening. As this solute particle goes into the solid state, you have another solute particle goes into solution. And that just continues back and forth in a saturated solution that's in contact with the solute in the solid state. So let's look at what happens in the formation of a specific solution. Now in this solution, what we're doing is making a solution of potassium chloride in water, all right? So you'll notice you have 100 grams of water here, and the temperature of the water is kept at 20 degrees, all right? So therefore, you're going to first add 5 grams of potassium chloride to the 100 grams of water, and that would be a solution, right? And then you add 10 grams total of potassium chloride, and that 10 grams of potassium chloride will dissolve as well. So therefore, you're going to end up with a solution, and that solution will be unsaturated. And then if you increase the amount of potassium chloride to 15 grams, then that will also be a solution. If you add 20 grams, you're still going to have an unsaturated solution. And then if you add 25 grams, you're still going to have an unsaturated solution. If you add 30 grams, you're still going to have an unsaturated solution. So therefore, basically, all of the potassium chloride, 30 grams of it, will remain in solution. Now, if you add 34 grams, what happens is that not all of it will dissolve. In fact, this is the maximum amount of potassium chloride that will dissolve, because at this point, the solution will be saturated. All right? So that's what happens in the case of potassium chloride. The solubility of potassium chloride, therefore, is 34 grams of the solute per 100 grams of the solvent. All right? So if you add another gram, then basically that extra gram will not dissolve. So therefore, no more potassium chloride can dissolve, because the solution has already achieved the saturation level at 34 grams of potassium chloride for 100 grams of the water. All right. So therefore, if you try to add any more potassium chloride on top of that, then basically the extra potassium chloride will not dissolve. All right. So the saturated solution is basically the solution where the maximum level of concentration of the solute is reached. Now, one thing you need to recognize is that if a solution is saturated, it can be either dilute or concentrated, and it all depends on the solubility of the solute in the particular solvent. So there are some solutions that are saturated but are very dilute, all right? But there are other solutions that are very concentrated and will be saturated as well. So basically, the level of saturation is different depending on the solvent and also depending on the solute, all right? Okay. Now, the solubility of a solute will change based on the temperature. Now, remember, previously, we had a temperature at 20 degrees Celsius. So if we were to change the temperature by increasing it, raising the temperature from 20 degrees to 50 degrees, then the 1 gram of the potassium chloride that did not dissolve will now dissolve, right? So therefore, at the temperature of 50 degrees, the saturation level will be about 35 grams of potassium chloride per 100 grams of water, all right? So in fact, to be perfectly accurate, this would not be a saturated solution. We know that it's a solution anyway, because the remaining 1 gram will dissolve, right? So basically the point here being made is that a solution that is saturated at one temperature may not be saturated at another temperature. And more than likely what will happen is that as the temperature increases, then the level of saturation would increase. In other words, the amount of solute needed for the solution to be saturated will be increased as well. Okay, again, the saturated solution could be either dilute or concentrated. All right. Okay. So we have our solution at 35 grams of potassium chloride for every 100 grams of water at 50 degrees. Now let's see what happens when we cool the solution to 20 degrees. So we're going back to the 20 degrees Celsius temperature level that we had before. So if we do that, cool from 50 to 30 degrees, then what's going to happen is that you're going to end up with a solution which is said to be supersaturated. Now remember, the solubility of potassium chloride is 34 grams per 100 grams of water at 20 degrees. But if you were to actually cool this solution here, which has 35 grams of potassium chloride per 100 grams, you will not find any solid potassium chloride forming from the solution, right? So we say that this solution basically has an excess of the solute present above the solubility limit. Now, that's a very unstable situation, all right? In fact, we call this solution a supersaturated solution. So a supersaturated solution is basically a solution that has more of the solute present than at the saturated level. And that's a very unstable situation, right? Basically, if you do literally anything to the solution, you'll have the spontaneous formation of your solute particles, all right? So as stated here, the supersaturated solution is unstable. So therefore, any stress, so if you, for example, simply tap the vessel with your finger or with anything, then you have the spontaneous formation of your solid potassium chloride out of solution, right? And basically that will happen until the solubility reaches a saturated level, which corresponds to the 20 degrees Celsius temperature. So that's basically an overall description using this example of the difference between an unsaturated solution, a saturated solution, and a supersaturated solution. So just to recap, a saturated solution is one where the amount of solute is less than the maximum needed in order for the solution to be saturated in a solution. A saturated solution would be the maximum solubility of the solute in the solvent, in a given amount of solvent. And then in the case of a supersaturated solution, the amount of solute present is above the saturation level, right? And that is very unstable. And therefore, any stress that is caused to the system will cause the spontaneous precipitation of the excess solute out of solution, all right? So that's the difference between those three types of solutions. Okay, let's talk about the rate of solids dissolving in a solvent. So the dissolution of a solute in a solvent is based on the particle size. And basically, when you have a solid that is in contact with a solvent, then the dissolution will be initiated at the surface that is in contact with the solvent, all right? Now, what you'll find is that smaller crystals will have a larger surface to volume ratio compared to larger crystals. So therefore, for that reason, in the case of smaller crystals, the area of contact between the surface and the solvent would be greater. And therefore, as a result, the smaller crystals will dissolve faster than larger crystals. And this is something, of course, that we should know or you should recognize from your everyday experience. So for example, if you're trying to dissolve like a block of sugar in water and compare that to dissolving the same amount of sugar but in the form of granules, then of course the granules will dissolve at a faster rate compared to the block of sugar. And that's because the granules will have a larger surface area in contact with the solvent compared to the larger block of sugar. Okay, so that is being demonstrated here. You have a larger block here of a particular solute, so this could be sugar, and you have a smaller block here, right? Now the surface area for the larger block will be 6 times 1 centimeter squared, provided that the length here is 1 centimeter across, right? It's a perfect cube, right? So there are 6 surfaces, so the total surface area would be 6 times 1 centimeter squared. Now, if you break this up into smaller blocks where each edge is 0.1 centimeters, then basically you're going to need, this will be broken up into 1,000 smaller cubes of this same size, right? And therefore, in this case here, the surface area for each cube will be 6 times 0.1 centimeter. I'm sorry, it's going to be, let me see here. It will be 6 times 0.01 centimeter squared. So therefore, the total surface area will be 0.06 centimeters squared. And you're going to have 1,000 of these, so therefore it's going to be 1,000 times 0.06 centimeters squared, which is equal to 60 centimeters squared. So basically, the surface area here, total, for the smaller cubes collectively, will be 10 times greater than the surface area of the large cube, all right? And what that means, therefore, is that the rate of dissolution of the smaller cubes in a solvent will be 10 times greater than the rate of dissolution of the larger cube because of the 10-to-1 ratio between the surface areas of the smaller cubes collectively compared to the larger cube. Okay, temperature. We talked about temperature affecting the rate of dissolution for solids. And as stated here, the rate of dissolving a solid increases with temperature in most cases. Now, this occurs because of what happens at the microscopic level. So what happens is that the solvent molecules will have more energy at higher temperature, and therefore they will hit the solid surface more frequently, and therefore there will be transfer of energy, which causes solid particles to break away from the rest of the solid, and therefore cause the solid to dissolve more rapidly in the solvent. All right, so that's basically the explanation as to why is it that the rate of dissolving of a solid or solute increases with temperature. So this graph here basically shows you the plot of solubility versus time. As you can see, as time increases, the solubility increases, but you'll notice that it plateaus after a while. And that's because at this point, you're going to end up with a saturated solution. Now, I think this is a plot for sodium chloride, if I'm not mistaken. I could be wrong. So basically, they didn't say what the solid is, but I think it's sodium chloride. So basically, this is how the solubility varies at time, all right? And you can actually determine what is called the rate of dissolution using this curve here. All you have to do, if you want to find the rate of dissolution at a particular point, let's say this point here is that you draw a tangent to that curve, and then you find the slope of that tangent, which would be the change in concentration divided by the change in time, and that gives you the rate of dissolution. And you'll notice that that slope flattens out as time progresses. So therefore, what that tells you is that the rate of dissolution decreases as time increases, right? It is relatively fast at the beginning, but the rate of dissolution decreases as time progresses, all right? So that is what happens when you look at the rate of dissolution of a solid in a liquid solvent. So that is what is being shown there. As the solid solution concentration increases, then the rate of the dissolving decreases, all right? Now, of course, in practice, when you are dissolving any solid in a liquid, if you want to maximize the possibility of the solid dissolve, then basically you would have to do some stirring. If you leave it to sit for a while, then it takes a longer time for the solid to go into solution, all right? So basically, and the reason why, of course, you do that is because you want to increase the amount of contact between the solid surface and the solvent, all right? So as stated here, as the solid dissolves, the amount of dissolved solute around the solid increases, and then the rate of dissolution or dissolving decreases, all right? So that's what happens when you have the solute going into solution, all right? But stirring, as I said before, increases the contact between the solute and the solvent. And therefore, that would increase the rate of dissolution more, and therefore, the solid will dissolve more rapidly in the solvent. Okay, so that's what happens when you stir it. The rate of dissolution increases. All right. Okay, so let me skip that here. And let me talk about reactions in an aqueous solution. So in this section, and maybe we won't get to it here today, but next class, we will get into some actual calculations where we look at the stoichiometry of reactions that are occurring in an aqueous solution. Now, let's talk about solids reacting with each other. Many solids, when you have a reaction taking place between two substances that are solid, what you'd have to do is actually put them in a solution in order for a reaction to take place. If you try to mix the two solids together, then no reaction will take place. So for example, let's say you've tried to mix silver chloride, which is a solid, with silver nitrate, which is also a solid, right? So if you try to mix these solids together, then no reaction will take place, right? And you'll wait forever and nothing will happen. Now, why is that so? Well, the reason why that is so is because the particles or the ions of the sodium chloride and the silver nitrate are basically securely locked in their crystal structure. They're not mobile, so therefore they can't move around in order to come into contact with each other and therefore cause a reaction to take place. So basically that's the reason why if you take solid sodium chloride and mix it with solid silver nitrate, no reaction will take place whatsoever. All right. Now, if you dissolve these two solutes in water, then you'll see the immediate spontaneous reaction taking place where a white precipitate is formed, right? And this is the reaction that will take place. The reaction will be the formation of this here, silver chloride, which is a solid, right? And the reason why this reaction will take place is because when you add these two to water, then the ions are now free to move around, and therefore the silver ions will freely combine with the chloride ions to form the silver chloride solid, all right? So therefore, we have a precipitate of silver chloride being formed as a result, all right? So that's the reason why a reaction will take place when these two solids are dissolved in water. The ions become free to move around and therefore will come into contact with each other to form the precipitate silver chloride. Okay, and also the sodium nitrate here, which remains in an aqueous solution, will simply float around and not react, all right? So basically the NaNO3 here actually exists as free ions that are basically floating around in the aqueous solution. Okay, so now we're going to get into some quantitative discussions when it comes to concentration. Now, there are several ways of expressing what we call the concentration of a solution. But let's define what we mean by concentration firstly. So here's the definition right here. A concentration or the concentration of a solution expresses the amount of solute that is dissolved in a given quantity of either the solvent or solution, all right? So that's a general definition of what we call the concentration. So let's talk about the difference between a dilute and a concentrated solution. So these are relative terms, and these are qualitative terms. They don't tell us exactly the amount of solute present in a solution, right? So basically, a dilute solution contains a relatively small amount of the dissolved solute, right? Whereas a more concentrated solution contains a relatively large amount of a solute in a solution. So as you can see here, these are basically relative terms, all right? Now, of course, quantitatively, we would have to use some numbers to express the level of concentration. So for example, what we normally call concentrated hydrochloric acid actually contains 12 moles of hydrogen chloride or hydrochloric acid for every 1 liter of solution, all right? So this is basically what we in chemistry consider to be a concentrated solution of hydrochloric acid. Now, in some labs, you might have, and we do have that downstairs actually in our lab here, you can have a solution of 6 moles, of hydrogen chloride for every 1 liter of solution. So this solution here would be more dilute, even though in practical terms, it's actually very concentrated, all right? But it is more dilute compared to the original solution here. And then we can also have another solution where the concentration is such that you have 4 moles of hydrochloric acid for every 1 liter of solution. So basically, these are 3 different solutions of hydrochloric acid where the concentrations are different. And basically, based on the numbers here, we can tell which one is the most concentrated. Which one is the most concentrated and which would be less concentrated. Get some water here again. Okay, so here. Okay, so let's continue to talk about the different ways of expressing concentration. And the first way is what we call mass percent solution. Mass percent solution. Mass percent solution. Now, what do we mean by that? By definition, it's basically the concentration of a solution expressed as the percent of a solute in a given mass of a solution. So basically, you're taking the mass of the solute, and in this case, we're using grams, and you're going to divide it by the total mass of the solution, right? Now, of course, this represents the mass of the solution, the total mass of the solute plus the mass of the solution. So basically, you take the mass of the solute divided by the mass of the solution in grams and multiply by 100, and that is, that is the mass percent of the solution. All right, so that's basically one way of expressing the concentration of a solution. So, for example, let's look at this question here. This question says, what is the mass percent of a solution of a sodium hydroxide in a solution that is made by dissolving 8.00 grams of sodium hydroxide in 50 grams of water? All right, so basically, what we have to do is find the mass of the solute, which is actually given, the 8.00 grams, and we need to determine the mass of the solution. Now, we're given the mass of the water, we're given the mass of the solute, which is sodium hydroxide. So the mass of the solution would be the sum of these two, right? So this is the equation that we use to determine the percent mass of the solution, percent by mass. So basically what we're going to do is take the mass of the sodium hydroxide and we divide it by the sum of the masses of the sodium hydroxide and the water. And when you do your number crunching, you end up with your answer being 13.8% by mass of the sodium hydroxide solution. So pretty straightforward. Basically, you're applying this equation here to answer this question, all right? Okay, any questions about this example? Any questions? Any questions? Okay, the next example I think I have lined up. Okay, why is this not moving? Okay, in this case, they gave you the percentage of the solution and they gave you the mass of the solution, right? So the question is asking, what are the masses of potassium chloride and water needed to make this solution? So this is the total mass, and this is the mass of the, this is the percentage of the solution. So this is the total mass, and this is the equation for calculating the mass percent, all right? So what I would do, firstly, is that I would rearrange this equation so that I can get an expression for the mass of the solute. So this is the equation right here, right? The mass of the solute in grams would be equal to the mass percent times the grams of the solution divided by 100. So we take the mass percent times the mass of the solution, which is 250 grams, divided by 100, and that gives you 12.5 grams of the potassium chloride. But we're not finished yet because the question is also asking for the mass of the water. So basically, how do we get that? Well, we simply subtract the mass of the potassium chloride, which is the 12.5, from the mass of the water, and that gives us the answer, which is 238 grams of water. All right? So that's basically how this problem is solved. Okay, any questions about this example? Any questions? Any questions? Okay. Hold on, let me see what this. Okay, so, this is just saying you dissolve 12.5 grams of potassium chloride in 238 grams of water to get a 5% solution. All right, so this is just describing how you'd actually make up the solution. All right, so here's another example. Now, this one is a bit more complicated because they gave you the percentage, but they also gave you the density and they gave you the volume of the solution. And the question is asking how many grams of sulfuric acid are contained in that volume of the solution. All right. So the first thing I would do is determine the mass of the solution in grams. Now we can do that because we're given the volume in liters and we are given the density of the solution. So this is the setup right here. We have densities equal to mass over volume. We can find the mass by multiplying the density by the volume. So we put the numbers in. 1 liter is the same thing as 1,000 milliliters, or 1.00 times 10 to the 3 milliliters. So that number would go here where the volume is, and the density is 1.25 grams per mil. So basically we multiply the 1.25 grams per mil by the 1.00 times 10 to the 3 mils, and that gives you the mass, which is 1,250 grams, which is the mass of the solution. But the question is asking for the mass of the solute, which is the sulfuric acid. How do we find that? Well, we take this mass, which is the mass of the solution, which we just calculated, per 50, or 1,250, and we multiply that by the mass percent. So basically, let's move this up here. So basically, we multiply the 1250 by the 34%, right? 34.0 grams divided by 100 grams, that's 34%. And when you do your number crunching, the answer is equal to 425 grams of sulfuric acid. So basically, to make up this solution, we weigh 425 grams of sulfuric acid, and then we dissolve it in, we add to it the amount of water to make a final mass of 1,250 grams. In fact, the amount of water that you would add, let me calculate that here. Hold on, let me see here. Whoops. Let me calculate that here. The amount of water you would add would be equal to 1,250 grams minus 425 grams. So let me use my calculator to determine what? To determine that 1,250 minus 425, and according to my calculation, this would be equal to 825 grams. So therefore, to make up this solution, you have to weigh 425 grams of the sulfuric acid and then add 825 grams of the water to it to make your final solution. All right? Okay, any questions about this? Any questions? Okay, so let's move on. You know what? Let me check something out here first before I move on to this. Let me go to, what did I do? Oh shoot, I closed it. Okay. Oh, okay, I didn't close it. Okay. Let me check something here. Go to files, close this, and then let me go to assignments, and then let me go to chapter 15. Let's see here, solutions. Let me download this here. Okay, I'm trying to see if you can do any problems based on what we have covered so far. Okay, I don't see, okay. You guys won't be able to do that one. Let me go here. Let me check out something here. Okay. All right. I'm going to stop here for today. I think I need to let me check something out here. Let me check 39 here. Oh, okay. You should be able to do, okay, I think I have this out of order. Which I must apologize. Percent by mass. Oh, okay. So you won't be able to do this either because we haven't done percent by volume yet. Okay. So what I'm going to do, let me check assignment 40 here for a minute. Come on, let me see. Okay. This is 40. Okay. All right. I'm going to stop here. You won't be able to do any of the assignments that are posted in Canvas. So I'm going to stop here for today. But before you leave, let me inform you that I won't be able to hold class on Wednesday. And that's because I have a meeting which I have to attend, which starts at 3 o'clock. And based on past experience, I'm quite sure that meeting won't end in time for me to come to class at 4. So basically, I'll be canceling that class on Wednesday. So there will be no class on Wednesday. We will meet again next week, Monday. Also, let me remind you that I've posted the test online if you haven't seen it yet. It's located in the test folder, which is located under the files link. So that is due on Friday at midnight. So make sure you complete it by then. Make sure you follow the instructions that I've posted in the announcements. For example, make sure that you upload it as a PDF document in Canvas and make sure that it is done in your own handwriting, no typewritten work. Make sure that it's in ink, blue or black ink, and so on and so forth. All right, so make sure that you get to that and complete it by Friday. Okay, are there any questions concerning what we have covered or generally the test? Any questions on the test or any questions in general? Any questions? Okay, so if there are no questions, that's basically it for today. So as I said before, we'll be meeting on Wednesday, so I'll see you guys next week, all right? So take care and have a good day.